Today we are going to discuss the drafting system of the air jet spinning machine. Now, what are the requirements in the drafting system of air jet spinning machines? There are two important requirements are there. One is it should be capable of giving very high draft, because we have to spin from a sliver. So, it is a sliver to yarn conversion process. So, sliver is quite thick and the yarn is quite thin, and we are directly converting from sliver to yarn, and hence the drafting system should be capable to provide very high draft, much higher than what we find in the case of ring spinning. The other thing is high speed. The machine produces at a very high speed, and therefore, the drafting system must have a capability to run at a very high speed in comparison to ring spinning. So, we have to have a drafting system which is capable to provide high draft as well as high speed. Both are important requirement of the drafting system that is used on air jet spinning machines, also on vortex spinning machines, and also we will find that this may be required even in the case of friction spinning machines, because roller drafting systems are used, and generally we feed a sliver, and therefore, the requirement is of high draft as well as high speed. Whereas, in the case of ring spinning, the requirements are low draft and low speed. So, these are the important differences. Now, question is, why do you need very high draft? Because to produce yarn directly from sliver, that is why we need very high draft. And this is the requirement, since speed frame or roving frame, which are normally used in the case of ring spinning process, where in between the sliver and the ring spinning we have an intermediate machine called roving frame, or sometimes called also speed frame. That machine has been eliminated here, and why it has been eliminated? Because it is costly. There is a capital cost in purchasing those machines. We need space and manpower. Then there are mechanical difficulty to adjust the machine and to set it, so that we can produce an intermediate product on roving frame, which is known as roving. Then it also consumes lot of energy and merely used to pack sliver in the form of a suitable for ring spinning. That is the purpose of the roving frame, was that it is used mainly to pack the roving in the form which is suitable for ring frame. Now, this is what we do not need now. So, for all purposes we need to eliminate this particular machine, and if we can produce directly from sliver, then there is going to we will be able to save lot of space, lot of capital cost, and lot of labor, energy, everything. So, there is a lot of advantage. That is why we try to go for high draft in order to eliminate the process of conversion from sliver to an intermediate product called roving. That is the reason. So, therefore, machine manufacturers are always thinking of developing a machine, so that we can directly spin a yarn from sliver. The other thing is, fibers in slivers are very they are straight and therefore and parallel, they can be drafted more evenly and more easily. But when we convert this fiber into roving, we twist it, and therefore that the straight parallel arrangement of the fiber is transformed into an helical arrangement of fibers in the roving. So, we can avoid that if we do not make roving at all, and if we have a system where we can directly spin from sliver, because in sliver fibers are perfectly straight and parallel, free from any twist, and therefore, they are very easy to draft also. So, these are the reasons. The question will come that how much draft we really require to spin directly from sliver. Now, roving frame draft rise in the range of 10 to 12. Ring frame draft, if we think it is lying in the range of 20 to 30, and therefore, total draft requirement from sliver to yarn could be to the order of 10 into 20 on the lower side 200, or it could be to the extent of 360. As an example, I am showing it. So, it means that if I want to convert a sliver into a yarn, the drafting system should be capable to provide a draft in the range of 200 to 360. That is the kind of draft that we require, or at least 150 or more than 100. That sort of draft is what is required. The other requirements for the high drafting systems are listed here. One is precision made drafting rollers, needle bearing, and perfect alignment of top and bottom rollers. This is what is required. Our drafting rollers has to be much more precision made. That means they should be, the eccentricity should be minimum. Then the bearing has to be much better, because the roller has to run at a very high speed, and the alignment of top and bottom roller has to be perfect. Now, we will discuss this now. Why the rollers have to be so perfect in terms of the manufacturing precision. First of all, the irregularity that is generated due to drafting wave is proportional to d minus 1. Relative variance, that is the irregularity is expressed in terms of relative variance, that is CV square, will be proportional to the draft. So, if the draft is high, the relative variance is going to be high, and it is linearly related. So, if we think of going for high draft, we have to remember that it will give us very high irregularity also. So, we have to try to suppress the formation of drafting wave. The other thing is, the eccentricity of the drafting rollers have to be minimum, as irregularity generated by the eccentric roller is proportional to the square of draft. If the rollers are eccentric, the percent amplitude in the mass per unit length because of eccentricity is k into d minus 1 into E by d. And what are these parameters? A is the amplitude of the periodic variations, d is the draft in the zone behind the eccentric roller, small e is the roller eccentricity, and small d the diameter of the eccentric roller. So, the amplitude of variation which is generated because of the roller being eccentric is proportional to the draft in the zone behind the eccentric roller, it proportional to the eccentricity of the roller itself and the diameter of the roller, which is eccentric. And therefore, relative variance here is going to be proportional to amplitude square, percent amplitude square, and amplitude square in turn will be proportional to d minus 1 E by d whole square. What does it mean? It means that if the roller is eccentric, the increasing the relative variance is going to be very, very high. So, a small change increase in eccentricity will make a big difference in the irregularity of the drafted sliver. After the sliver is drafted, whatever fleece we generate out of it, that will be highly regular, because it will be proportional to the draft and is proportional to the square of draft d minus 1 whole square, and also proportional to the eccentricity square. So, therefore, eccentric roller means too much generation of irregularity, and therefore, if in a high draft system we have to go for high draft, there we can't reduce the draft in order to reduce the irregularity generated because of drafting wave, because that option is not there. But what is there in our hand, that any other mechanical fault that can generate irregularity, can we reduce that or not? And there the option that we have with us is the value of E, that is, the roller should not be eccentric, or eccentricity of the roller should be much less in comparison to the kind of roller that we can have on ring spinning drafting system or roving frame drafting system. And hence, we write that we need precision made drafting rollers and their needle bearing. Needle bearing will also consume much less energy, and the alignment is another important requirement between top and bottom rollers. So, all these are therefore they become very important for high drafting system to be successful. The other requirements are high quality aprons and cots. High speed of apron causes premature wear of the aprons and to the roller cover, that is the cot, because the speeds are much higher in this case, and as a result the aprons will be wearing out faster, the top roller cots also will wear out faster. Hence, we need high quality aprons and cot both, so that they do not wear out so fast. The other thing is sliver guidance within the drafting zone. High speed of the delivery rollers can produce air current which causes the fiber fringe to spread out between the aprons and the delivery rollers, leading to poorer yarn quality. With the high speed, because the air current gets generated with speed, the air current is powerful enough to disturb the array of fibers which are basically moving within the drafting zone, and if they are displaced from their original position because of the air turbulence, then it will actually be seen in the yarn in the form of lot of faults. So, the quality of the yarn will be downgraded, and hence to avoid that, what we can do is that we can have sliver guidance within the drafting zone, so that the synchronous movement of the guiding elements like condensers and sliver guide placed behind the back roller is what is required. So, that we try to ensure that the spreading is restricted by having a sliver guide at the feed point and then also a guiding element or condenser in the drafting zone. So, we do not allow the drafted material to be to spread out too much. That is what will be required. Other thing is the cleanliness of the drafting system. Efficient suction system to keep the rollers and the bearing clean. So, because the speed are more, so whatever suppose dust is there in the fibers, so that dust is going to accumulate on the different parts of the drafting system, and they can actually create problem with the normal processing of the fibers. So, we have to keep the entire system clean, and for that we need very efficient suction systems, so that the rollers are clean and the bearings are also clean. So, efficient suction system is also required in this case. So, these are the important requirements. So, you will find that the high speed drafting systems which we have on air jet spinning machines, they are superior in these respects. Otherwise, this is also a basically few pair of rollers are there, either 3 pair of rollers or 4 pair of rollers are there. So, to a layman, a drafting system of air jet spinning machine or a drafting system of wing spinning machine will appear to be similar, but the difference exists in terms of quality of the rollers, the guidance system that we have, and the kind of cleanliness that we require. Then only the drafting system will be successful. These are the requirements. So, accordingly, all the drafting elements are manufactured. Now, we will come to the analysis of high speed drafting. We all know that any drafting, especially with cotton, where the short fibers are present, leads to generation of drafting waves or a kind of irregularity, which we cannot avoid because the short fibers are there. Now, we will study something here. We will try to analyze the high speed drafting system, where the fibers are withdrawal at a very high speed from the slower moving fibers. So, ultimately drafting is a basically change of speed of the fibers. So, there is a two groups of fibers, some fibers are moving at slow speed, some fibers are moving at high speed. So, there is a transition where the speed is changing from slow to high. Now, this transition is a place where there is a possibilities of creation or generation of, you can say, some kind of disturbance in the motion of the fibers. Now, what happens in the case of high speed drafting? We will try to analyze that. In slow speed drafting, the acceleration pattern of short fibers within a drafting zone varies in an uncontrolled manner. That is, the acceleration pattern is changing continuously, and there is no control on that, and that leads to generation of irregularity. It is partly suppressed by aprons. So, the very purpose of the aprons is that the acceleration pattern is changed, that we will allow the fibers to accelerate when they reach the nip of the front rollers, and therefore, some guidance is given in the with the help of aprons. Aprons will physically grip the fibers and will actually guide them through the drafting zone and make sure that they get accelerated only when their front end is nipped by the roller of the front rollers. Otherwise, this will not accelerate out of turn. The other thing is, if the pulling force acting on a fiber is sufficiently high, then the fiber can be pulled away without disturbing the arrangement of the remaining fibers. So, if there is a bunch of fiber like here, one fiber which is this one, if we pull it out at a very high speed, then the arrangement of the fibers left behind is not going to be disturbed because of the inertia. So, everything depends upon the speed with which one fiber is withdrawn from the rest of the fibers. And for that, what we need is the pulling force on a fiber must be much greater than the static frictional force between fibers. So, P is the pulling force and static frictional force between fiber is F. So, P, if it is much more than the static frictional force F, then the fiber will be withdrawn without disturbing the arrangement of the fibers which are left behind. Now, this is what is important, and we will try to understand this now, that what is the value of pulling force and how can I find out the value of the static frictional force. The estimation of the pulling force, first of all, let the mass of a fiber be m and V1 is the incoming velocity of the fiber, V2 is the outgoing velocity of the fiber, A is the acceleration, that is as the fiber changes its velocity from V1 to V2, that has to be some acceleration. So, that acceleration is A, and S is the distance over which the velocity increases from V1 to V2. Assume the fibers to be solid rods. So, the pulling force acting on a fiber is going to be mass into acceleration, P is going to be m into A. M is the mass of fiber, and what is the fiber mass? Fiber mass is basically this one. If L is the length of fiber, F tex is the fiber fineness in tex, and G is the acceleration due to gravity. So, F tex into L will give you the weight of the fiber, and that divided by G will give you the mass of fiber. We have to make sure that the units are compatible, then we will directly get the value of, we will get m from the values of the text value of the fiber and the length of fiber. So, length and text value of fiber, from there if we multiply you will get the weight, and the weight divided by the gravitational acceleration will give you the mass. So, m is this. So, P becomes m into A. So, m is basically this one. Now, we go to the next page, that is estimation of fiber acceleration. So, mass, so we can find it out. Now, what is the acceleration of the fibers? Now, here first of all, the energy required to transport a fiber over a distance is basically change of kinetic energy. That means, m into A into S equal to half m V2 square minus V1 square, because the speed is changing from V1 to V2. So, force into displacement, this is the force, S is the displacement. So, this side is energy and the right hand side is also kinetic energy. So, they can be equated, and from there we can find out what is the value of A. So, A becomes 1 upon 2 is V2 square, V2 minus V2 square minus V1 square. I divided it by both the term by V2, and therefore, it becomes 1 minus 1 upon d square. That is, I am dividing V2 square by V2 square, V1 square by V2 square, and because I am dividing it, I am bringing V2 square in the numerator. If by doing so, I can change the expression within the bracket that we have. That expression has been changed, and we have now got the value of the draft D, where D is the ratio of V2 by V1. Now, when D is quite high, that is D is suppose greater than 30, then 1 upon D square becomes 1 upon 900. So, 1 upon 900 is very low value, is almost, so 1 minus 1 upon 900 is almost close to 1, and therefore, the value of A becomes 1 upon 2s V2 square, and practically it becomes V2 square by 2s, because 1 upon D square becomes, this becomes quite close to 0. So, A become V square by 2s. Substituting this value of A in equation 1, we can write the pulling force P is V2 square by 2s, that is basically A, and this is the mass of fiber, this is M, and this side is A. Now, the frictional force between the fibers. For that, what we need to do? We have to take a sliver and actually test its strength on a tensile tester. So, frictional force can be estimated from the high speed tensile test of a sliver keeping a gauge length greater than the maximum fiber length. Like it is shown here, that here is a sliver, and this GL stands for gripping length or gauge length. Now, if we gauge length is much larger than the length of the fiber, so that not a single fiber will be able to span from gripping line G to gripping line H. All the fibers should be shorter than this, and then we go for high speed tensile test. So, we will get some value of the strength of the sliver. Let L becomes the breaking length of sliver in meter, that is the length of sliver which will cause the sliver to break if it is hung. So, if it is hung, then due to the, if the length is L, at this length the sliver is going to break, that is called the breaking length, and N is the number of fibers in the sliver cross sections. And B is the sliver breaking force. The sliver breaking force is the force required to pull out N fibers, and that is going to be basically B, where B is going to be the L into N into FTX. What is N into FTX? N into FTX is basically the sliver linear density or sliver text value of the sliver. Number of fibers in the cross section multiplied by the text value of the average text value of this fiber will give you the sliver linear density. So, that multiplied by L, the breaking length of sliver, will give you the breaking force of the sliver. We will get the breaking force of the sliver B. From now, force required to pull out a single fiber gripped by the jaw during tensile test can be found out. B is how much? B by N, or we have already found out the sliver strength is L into N into FTX. So, B by N is going to be L FTX. Now, during tensile test of a sliver, only half the fiber length becomes effective. When we remove, suppose this is the sliver, this is going in this direction and this jaw is going in these directions, or this jaws may be stationary. Even if it suppose if I say that this jaw now is not moving, the other jaw is moving. So, fibers are getting separated from each other. Now, when it gets separated, the number of fibers which are gripped under a jaw G or suppose this jaw. Now, what we have done in the next diagram, what we are showing this jaw which is, let us say, going which is separated bunch of fibers in this jaw. So, this is the after the sliver has broken, these are the fibers gripped by the gripping line of the jaw at the point G, and now these are the fibers which are projecting out on the right hand side. Now, if I arrange these fibers in order of decreasing length, then we get a picture like this. Now, in this picture, what we find that the length of fibers which are gripped here, the length which is on the left hand side of it is basically will be how much? Will be whatever is the total length of fiber, only half of it on an average is actually projecting on the left hand side. So, if the number of fibers are n, that is fine, that does not change, but if the length of fiber is, each fiber is small l, the total length of fiber is n into L, but the fibers which are on this side is actually n into L by 2, and on the other side also similarly it will be n into L by 2. So, these fibers are basically n into L by 2, because there is side fiber here which is projecting out the left hand side almost 0, the next one is only this much, next one is only this much, this is the maximum length which is projecting out. So, on an average we can say the left hand side projecting out fibers is only L by 2. Therefore, when the separation takes place, actually half the fiber length is participating in it, and therefore, frictional force required to pull out one entire fiber, but when I try to remove one fiber from the rest of the sliver, then the entire fiber length has to be pulled out, because rest of the fibers are actually surrounding the fibers which is being pulled out, and therefore, the frictional force required to pull out one entire fiber is going to be not L F T x, but twice L F T x. That is the difference. So, I am pulling out one fiber from rest of the other fibers which are surrounding it. From there, we can write now that for non-disturbed drafting, P has to be greater than F. This is the conditions. If P is much higher than F, that is static frictional force, then that fiber will be withdrawn and the rest of the fibers will remain in their position, they will not get disturbed. So, P has to be more than F, and that basically means V squared by 2s F T x L by G has to be greater than 2 L F T x. So, this is the condition we have to meet, and from there we can say that basically means that V 2 square has to be greater than 4 small s capital L G by L. Say F x and F x will cancel on both sides. So, V square is going to be 2 into 2, this will be 4, s and g will go to the numerator, L remains what it is and small l comes in the denominator. So, we will be left out with this equation, that is V 2 square has to be greater than 4 into small s is the distance over which the fiber is accelerating, and capital L is the breaking length of sliver, small l is the fiber length that we have chosen, and g is the acceleration due to gravity. So, from there, okay. Now, from there what we are doing? We are trying to solve a simple numerical example. What is stated here? That from the following data, calculate the velocity of fiber withdrawal. G value is been given, sliver breaking length is 15 meter, this is drawn sliver, so its breaking length is much less. A cut sliver is much more stronger, or a drawn sliver is going to be very weak, it is a twice drawn sliver. Sliver linear density is 3 kilotex, the sliver is practically quite fine. Fiber length is 40 mm, fineness is 1.5 decitex, and S has been considered to be 3 mm, that is displacement over which it gets accelerated is 3 mm. So, what is going to be the value of V2? So, first of all we are calculating what is the strength of the sliver. First of all, number of fibers in the sliver cross section is sliver tex by fiber tex. This simple formula that gives you a figure 20,000. That means there are 20,000 fibers are there in the cross section of the sliver, and the force, sliver breaking force F, or no, not sliver breaking force, the force that you need to withdraw a fiber, F equal to twice L into tex value of the fiber, tex F, or no, earlier I have written I think F tex, meaning basically same. So, whether F tex and in this case tex F are basically same. So, this is the force that you need to withdraw a fiber following the previous same expression I am using, and that gives you a value 4.5 gram force. So, the velocity of withdrawal has to be again using the same formula, other formula that we have deduced earlier. So, V2 square is 4 SL small g by small l. So, these values I am just substituting and getting a figure V square to be 11.02. This will be velocity square. That means, this unit is going to be meter square by second square. And then V2 is going to be therefore root over 11.02, and that gives you a figure 3.32 meters per second, and I convert it into meters per minute multiplied by 60, this gives you a value 199 meters per minute. So, it gives you an idea that if I maintain a very high speed of withdrawal, in this example the withdrawal speed is almost 200 meters per minute, then the irregularity generation because of the drafting wave is going to be much less. So, even though the draft is very high, because the speed is also simultaneously very high, therefore, the irregularity that we normally expect when you go for higher and higher draft, that will not be there in this case. So, the yarn will be quite regular. Otherwise, in the ring spinning kind of system, where if we try to go for higher draft, but the speed we do not change, then there irregularity will be quite high in the yarn, and that will not be acceptable in the market. So, if the draft is high, but speed is low, it will not work. But if the draft is high and speed also is high, then irregularity is not going to be more, irregularity will be practically same or may remain little less. So, therefore, the high delivery speed is beneficial, but for that we have to see the roller has to be more eccentric. So, other precautions that we have to take and other countermeasures we have to take in order to make sure that the aprons have a reasonable life. So, apron quality has to improve and the quality of cords has to improve, and lot of turbulence gets generated. So, a lot of dust gets settled on the drafting system, either dust from cotton, even the dust fibers, dust from other fibers also. The spin finish will, if we try to process synthetic fibers, the spin finish will also deposit on the drafting system, and hence we need a very efficient cleaning system, and that needs basically some kind of suction arrangement. So, suction arrangements are must for such kind of drafting system. So, high depth system, some figures are given here in this table. So, we see that most of the drafting system are either 3 roller or 3/4 rollers are also there, and 4 rollers are also there. So, these are the 3 types of drafting system by different machine manufacturers, and we have 3/3, 3/4, or maybe just 4 rollers as 4/4 type of systems are there. And draft range could be anywhere between 100 to 300. The delivery speed could be in this range or maybe more in the recent times, because there is always some improvement which is happening on these machines. So, speeds are increasing. The hardness of the top cord is to the order of 82 plus minus 2 degree shore hardness, and some typical speeds are given here. So, it is not that the speed is fixed at this level, speed range is also there. So, these are the delivery speed range typically. So, one can vary the speed in this range, even in some cases it can go up to 400 meters per minute also. And the draft is distributed into break draft, intermediate draft, and the main zone draft. This is how the draft could be there if it is a 3 zone drafting system. It is just a typical values have been given here, but it may vary from machine to machine, from manufacturer to manufacturers. In Murata twin spinner, the width of the cords this has been increased to accommodate what? Drafting of 2 slivers simultaneously. CMTS Murata twin spinner, that means I am drafting 2 slivers simultaneously. Therefore, the width of the drafting rollers has to be more, because 2 slivers have to be, we have to feed together, and sliver guides are provided behind the back roller and between the back roller and the apron to avoid riding of 2 slivers one above the other. To avoid that, so some guidance is required. So, this will never get entangled between themselves. That is the important thing. The other thing is also it will restrict the width of the drafted fleece that will ultimately produce. See, drafted fleece also is important here. We will study, we will see that the width of the drafted fleece is something which is very important in the case of air jet spinning. Like we want the width to be more, whereas in the case of compact spinning we want the width of this drafted fleece, or you can say the sometimes it is called also we can say the delta zone of the spinning, that width should be as low as possible in the case of compact spinning, but in the case of Murata air jet spinning system it has to be just opposite. It has to be widened, not less. So, we will study that why do you need a wider spinning triangle in the case of air disc spinning system, whereas we need a very small spinning triangle in the case of compact spinning system. So, requirements are different. In the case of air disc spinning, we need basically wider spinning triangle. So, we have to understand why we require this gradually. The next thing which is important is air flow around the drafting rollers and their influence. Let us say the surface speed of the front roller is 200 meters per minute. A typical speed we have chosen 200 meters per minute. It could be 150, it could be 220 also, it could be 300 also. So, one speed I have chosen as an example. Now, rotational speed of the roller is going to be in this case how much? 2500 rpm. So, the front roller will be rotating at a speed of 2500 rpm if it is producing at the rate of 200 meters per minute. So, the roller speed is extremely high, almost 10 times than the speed of the front roller on ring spinning drafting system. There the speed could be 250, 280 rpm in that range, because there the linear speed or surface speed of the roller is to the order of 15, 18 or 20 meters per minute at the most, and here it is 10 times of that. So, rotational speed also is very high. At this high rotational speed, some problems will be generated and we have to tackle those problems. One is, at such a high speed, the roller picks up air current and the boundary layer of air around the roller also will rotate, as it is shown here. No, the top roller and the bottom roller, you see these arrows are indicating that the air, how the air surrounding the roller is also moving. If a roller rotates at a high speed, these layers of air surrounding the roller will also rotate at a high speed. Immediately the boundary layer will have maximum speed because it is close to the surface. As we go away from the boundary layer, the velocity is going to be less and less. That means, whenever a roller rotates in the medium of air, as the roller rotates, the boundary layer also rotates along with the air. And what happens because of this? The boundary layers, that is with the top layer, and the boundary layers of the bottom layer, these two boundary layers are actually meeting each other at the nip of the two rollers. Now, when they meet at the nip of the two rollers, they cannot pass through the nip line, because the top roller is covered by a cot and the bottom roller is made of steel. So, between them there is a pressure and the nip is such that there is no escape route for the air to pass through, it is completely sealed. So, this air current which is there cannot really pass through the nip, and therefore, they will start moving along the nip as it is shown here. The airflow directions are now shown. So, these two air currents, which is quite powerful because the speeds are very high, they meet at the back of the top and bottom rollers, and because they have no way to escape through the nip, they will move sideways both sides, and this movement of this air is going to disturb the flow of fibers, the air flow. Whatever fibers are there now here, these fibers which are flowing here, let us say these are the fibers. These fibers are going to reach the nip and they will be gripped by the nip, but while they are trying to arrive at the nip point, the airflow is going to divert them. So, some fibers will, from the straight line path, they will bent a bit. So, the drafted fleece is going to widen because of this air current behind the nip of the two rollers, and hence the spinning triangle is going to widen. Now, if the current is too powerful, then this can disturb the flow of fibers, and as a result it can affect the quality of the yarn also. We want the spinning triangle to be wide, but at the same time we should make sure that it is not too wide or the fiber arrangement is not disturbed by the air current which is generated because of the rotation of the rollers. So, the disturbance that gets created is basically a function of or proportional to surface speed square. Small change in speed, surface speed, can make a big difference in the way the fibers behind the rollers are moving, and therefore, it can really affect the regularity of the yarn. So, thus the possibility to increase the drafting speed further is limited because of these reasons, and manufacturers are also thinking of going for higher and higher speed. So, what has been done is going for grooved front top cot. So, the top cots that we have on the front top roller is having grooves on its surface, and these grooves will allow the air at higher speed to flow through the cot, because where the groove is located the nip is not there. So, there is a passage for the air to pass through. So, you allow some air to pass through by having grooves on the surface of the top roller, and that way we can control to some extent the flow of this air along the nip line. So, these air escaping grooves reduce the disturbance by allowing air flow to pass through the groove. So, and because of this we have been able, or the companies have been able to raise the speed of drafting further. So, that is what kind of development that has happened in the basically cots design, that the cots are having now some grooves. With this, I think we close this session on drafting. So, otherwise whatever drafting you have learned while studying the ring spinning machines or while studying the speed frame or roving frame, practically it remains same, and the only difference is here speeds are high, draft is also high, and because of these two there is possibility that it can drafting regularity could be very high, but as we have shown that a high speed does not necessarily mean a high draft in combination with high speed may not generate so much of regularity as one would otherwise expect. But this is very sensitive, the irregularity generation is also sensitive to the mechanical fault of the rollers and the gears and the bearings. Therefore, the rollers, bearings and the gears which are driving the rollers, everything has to be much more precision made in comparison to what we have in the case of normal ring spinning machines. And I think with this we close this particular topic of drafting on air-jet spinning machines, and the drafting system for vortex spinning machine also practically same, and even a similar drafting system is also used in drape 3 friction spinning machines. Okay, with this we close today's session. Thank you.